Lecture 3, Praseodymium, the quiet strength in alloys. Picture a magnet maker in a nondescript industrial park, standing over a bin labeled the thing they actually need and the thing they cannot avoid, neodymium praseodymium oxide. They were hoping for neat, single-element ingredients, like a pastry chef lining up butter, sugar, flour. Instead, it is a blended bag. The flour comes pre-mixed with a little rye, and the recipe has to bend to the bag, not the other way around. That is praseodymium's first lesson. You do not so much buy praseodymium as you inherit it, bundled with neodymium by geology and by the frugal logic of separations. In the real world, the path from rock to rotor rarely offers pure choices. Let us introduce the green twin. Praseodymium is the lanthanide with atomic number 59, a soft, silvery metal that blushes to green as it oxidizes. The twin nickname reaches back to the old misidentification, didymium, once thought to be a single element and later revealed to be two, the purple-tinged neodymium and the greener praseodymium. If you have ever seen glassblowers' goggles that seem to cancel the yellow glare of sodium flare, you have seen didymium as a filter. Those spectral fingerprints come largely from how neodymium and praseodymium swallow very specific slices of visible light. Praseodymium's oxide has a characteristic green that turns up in ceramics and specialty glasswork, not because someone decided green is pretty, although it is, but because those absorption bands are useful when you need to see your work through the heat. Chemistry first, in plain language. Like all its lanthanide siblings, praseodymium's personality is set by the F electrons tucked into the fourth shell. In ordinary compounds, praseodymium likes the 3+ charge state, meaning it tends to give up 3 electrons and join the world as praseodymium 3+. There is a less common 4+ state that chemists coax out under oxidative conditions, but the stable workhorse is 3+, and that sameness, across the lanthanides, creates the processing headache you will hear about soon. On the bench, praseodymium is reactive enough to tarnish in air and fizz along with acids, but not so reactive that handling it requires theatre. It is magnetically interesting in compounds and intermetallics for reasons that have nothing to do with its glamorous twin. The way its electrons align can enhance the performance of permanent magnets at the temperatures that actually matter for motors, which is not room temperature but the hot, vibrating world under a hood or inside a wind turbine nacelle. Now, where does praseodymium actually live in the crust? You do not mine praseodymium ore. You mine minerals that quietly carry a lanthanide bouquet. The big historical source is bastnasite, a fluorocarbonate common in alkaline intrusions and carbonatites. Bastnasite, in places like Bayan Obo and Mountain Pass, concentrates the lighter lanthanides, lanthanum through neodymium, and with them, praseodymium. Another major host is monazite, a phosphate mineral that also favors the light side of the lanthanide family. Monazite tends to cohabitate with grains of minerals you do not want as houseguests. Thorium and uranium tag along, so the geology already invites regulatory friction when you try to crack the stuff open. Iron adsorption clays in southern China, which people associate with the heavier lanthanides, are not where you go looking for praseodymium in bulk. If your project is praseodymium and neodymium at scale, your map has carbonatites ringed in red, and your mineral names start with a B and an M, bastnasite, monazite. Take a quick walk through the rocks. Carbonatite intrusions are unusual, carbonate-rich magmas that pushed up from deep in the mantle and froze into the crust. They can be remarkably enriched in rare earth elements compared to normal rocks, which is why 0.1% in a vast tonnage suddenly matters. Over geologic time, weathering helps by liberating and reconcentrating these minerals in placers, making monazite sands if the setting is right. If you are a mine planner, you care less about the romance of mantle plumes and more about grain size, liberation, and whether the gangue minerals will play nice with flotation reagents. But under it all sits the same truth. Praseodymium is not rare in the sense of scarce, it is rare in the sense of stubborn. It is everywhere and nowhere, spread thin, chemically entangled. By the numbers, the United States Geological Survey estimated that world mine output of rare earth oxides was about 390,000 metric tons in 2024, with known reserves north of 90 million tons. Praseodymium is in all of it, abundant but unwilling to stand alone. Processing is where stubborn turns to expensive. Suppose your ore is bastnasite. You crush and grind to liberate the rare earth mineral from the gangue, often carbonates, fluorites, barytes, then float it to a concentrate. Then you deal with the fragility of the fluorocarbonate itself. Roast to drive off carbon dioxide and to change the mineral to something acids can chew. Sometimes a chlorination step, sometimes an acid bake, it depends on the flow sheet and on the impurities. Either way, the immediate goal is not praseodymium metal in hand, but rare earths in solution. Once they are in solution, they are together and annoyingly similar. Solvent extraction, hundreds of mixer settlers in long banks, like steel centipedes, is the usual next chapter. With carefully chosen organic extractants and painstaking pH control, you load the rare earth cations into an organic phase, strip them back into an aqueous phase, and repeat, over and over, inching toward purity with the patience of a watchmaker. Somewhere in those banks, cerium is pushed out early by oxidizing it to cerium 4+, which behaves differently. This is not just chemistry trivia, it is what opens the line to the twins you care about. Lanthanum likewise tends to peel off near the easy end of these trains, not because it is unwanted but because it is so abundant that it would otherwise crowd everything. Both of those siblings are so plentiful that their prices have collapsed to almost trivial levels, on the order of $1 per kilogram for lanthanum or cerium oxide, flooding catalyst and glass polishing markets with cheap material. Stripping out lanthanum and cerium early clears the stage for the elements that pay the bills. The stubborn twins, neodymium and praseodymium, are pried apart late, if at all. The similarity of their ionic radii and their nearly identical coordination chemistry make the separation costly, which is why industry so often waves a hand and says, "Fine, sell the mixture." Switch to monazite and the verbs change but the plot does not. You crack monazite with a hot caustic digest, sodium hydroxide in a cauldron, turning a refractory phosphate into a friable powder and liberating rare earth hydroxides. The phosphate leaves as trisodium phosphate, useful in itself, and the rare earths go into solution with acid. Now you are back in the centipede, walking solvent extraction lines. Along the way, you cannot ignore the thorium and uranium that monazite drags along. You do not wish them away, you account for them, capture them, permit them, and pay to store them. That is not an afterthought, it is core to whether a project gets a green light, because the chemistry does not accept your feelings about radiation. If this sounds unglamorous compared to the sleek photos of wind turbines and electric motors, good. One of the accurate ways to think about praseodymium is to forget the gleam of the final product and picture a very long hallway of wet chemistry. Each door you pass through, another extraction stage, adds yield here, purity there, cost everywhere. In that hallway, praseodymium's defining trait is how closely it hews to neodymium. The two are not chemically identical, but they are suspiciously close in all the ways that matter to separations. If you have ever tried to sort a bowl of nearly identical green and slightly less green candies while wearing oven mitts, you get the vibe. Industrially, the oven mitts are real constraints, capital, footprint, reagent consumption, and the reality that the product the market actually buys, especially for magnets, is the combined oxide because it keeps the whole machine simpler. Why should a magnet maker care? In a neodymium iron-boron magnet, the lanthanide sublattice is the soul. It sets the magnetic anisotropy, the preference for magnetization to lock into a specific axis, and the coercivity, which is resistance to demagnetization. Swapping a portion of the neodymium for praseodymium tweaks those properties in small but meaningful ways that designers exploit in the real operating envelope. The decision is rarely about absolute maximum performance in a laboratory, it is about stable performance at the high temperatures where motors live, and about supply realities. A blend of neodymium and praseodymium is not a compromise so much as a design regime. You buy the mixture, you set your alloy recipe accordingly, and you get on with your life. If your motor is an automotive traction motor that will see summer traffic, mountain grades, and a driver who insists on flooring it, your magnets must hold their nerve while hot. If your magnet is in a drone that must be quiet and efficient at altitude on a cold morning, you want a slightly different flavor. Those knobs, grain size, diffusion of heavy rare earths at grain boundaries, and which twin you favor, how praseodymium earns its rent. Praseodymium also wins a quieter race in glass and ceramics. A small amount of praseodymium in glass can transmit a precise red while swallowing yellows, which is magic if your job is to make a red glass that does not wash out in daylight. If you want to see past the orange-yellow glare of sodium in a hot flame, you put praseodymium with neodymium into goggles because they swallow that glare while letting the rest of the world through. In arc lighting, praseodymium compounds feed emission lines that read as vivid greens and yellows, and in optics, praseodymium-doped glass and crystals are part of specialty laser systems that do not care about fashion but about exact wavelengths. In magnesium alloys for aerospace, a pinch of praseodymium can change creep resistance and high-temperature strength enough to matter. Even hydrogen storage alloys and nickel metal hydride batteries quietly include praseodymium in their formula, as part of the lanthanide cocktail, mesh metal, that soaks up hydrogen, though lanthanum usually steals that spotlight. None of these markets are as gluttonous as magnets, yet they matter because they diversify demand and because they highlight a theme. Praseodymium is a tuner, and tuners have work in any orchestra. Rare earths are pigments and dials. They turn knobs the rest of the periodic table does not reach. If you need to nudge color, or light, or magnetization, or catalytic selectivity just so, the lanthanides are where you shop. Let us go back to the ground for a beat, because you should understand the bottlenecks in words, not flow diagrams. Beneficiation, the step where you separate valuable minerals from waste rock, is straightforward if you have coarse, well-liberated bastnasite and a cooperative gang. It can be miserable if the grains are locked, if clays smother your bubbles in flotation, or if barite and fluorite insist on tagging along. Chemical processing to move the rare earths into solution is chemistry that refuses to be rushed. If you are roasting, you must balance temperature high enough to decompose carbonates without wrecking the rare earth phase. If you are acid baking, you must balance acid strength and time against silica gel formation that will make filtration a nightmare. In solvent extraction, the organic reagents age and degrade, crud forms at the interface, the mixer settlers need maintenance, and the control room is basically a pH vigil. If your water is scarce, as it often is where these deposits sit, the cost of recycling and the penalty for losses both rise. If your electricity is expensive or erratic, the economics wobble. And if your permitting regime treats thorium as a showstopper rather than a manageable byproduct, then monazite, chemically attractive as it is, becomes a political liability. Now the supply chain reality, stated plainly. Control does not sit at the mine gate. Control sits in separation plants and in magnet alloying and powder-making facilities. Mines that produce bastnasite or monazite concentrates are plentiful on paper, projects labeled mixed rare earths dot the world. But the number of places that can march those mixed rare earths all the way through to separated neodymium and praseodymium in the purities and volumes magnet makers require is a tiny club. And within that club, the default product is a combined neodymium-praseodymium oxide. Because it is the efficient stopping point. The separate praseodymium stream exists, but it is a child of demand and of willingness to pay for the extra bank of mixer settlers and the extra control complexity. That is not a moral complaint, it is the engineering truth of like chemistry. For example, the United States mined on the order of 45,000 tons of rare earth mineral concentrate in 2024, but only about 1,300 tons of refined NdPr oxide was separated domestically that year. The rest of the material had to find its way to places with the requisite hallways of solvent extraction. That gap between ore and oxide is where the bottleneck lives. There is an almost comic, very human side to this. On one end of the chain, a geologist holds a piece of bastnasite and talks about alkaline magmas and phenatization and late-stage fluids. On the other end, a motor designer worries about demagnetization curves at 150 degrees Celsius and what happens after 10,000 thermal cycles. In the middle, there are people who care, with medieval fervor, about 30 millivolts of pH and the cleanliness of an organic phase. Praseodymium connects them whether they like it or not, and the point where control concentrates is rarely the one that makes for good press photos. If you want a concrete bottleneck stated without jargon, separating neodymium from praseodymium is expensive because they behave almost the same in the solvents we use to separate them. That sameness forces long banks of equipment and tight control. Each extra 9 of purity costs you an extra slice of capital and operating expense. This is why most magnet producers are perfectly happy to plan around a blended neodymium-praseodymium feed. They do not crave purity for its own sake, they crave consistency and supply. Let us touch processing one more time, but through the lens of what actually constrains startups. If you announce a rare earths project and your slide deck glows with neodymium and praseodymium, the magnet market leans forward. Then the diligence begins. Do you have a flowsheet that handles your specific gangue minerals, or did you copy one from a deposit that looks similar on paper but differs where it counts? Grain size, liberation, fluorine content. Do you have a plan for acid supply and neutralization, with real numbers for lime or limestone needs and a place to put the gypsum? Do you understand that solvent extraction at commercial scale is a discipline, not a bullet point? And do you have a buyer who will take a combined neodymium-praseodymium oxide at a price that acknowledges you did not spend another year of capex to strip the twins apart? If the answer to those questions is yes, you might get to day one of production. If the answer is, we will learn on the fly, you are, politely, describing tuition. Why praseodymium wins anywhere is never because of a single number on a datasheet. In magnets, the performance comes from the crystal structure that the lanthanide stabilizes and from the way that structure resists having its domains flipped when hot and under load. In glasses and ceramics, it is those narrow, quantized FF transitions that grant rare earths their weirdly specific colors. In alloys, think high-performance magnesium for aerospace. Adding a sprinkling of praseodymium can change creep resistance and high-temperature strength enough to matter. The microphone check answer is, praseodymium is a tuner. It is not the loudest instrument, it is the person at the mixing board who nudges the sound into clarity. One last piece for this opening pass, the human constraint of water, energy, and community. Rare earth chemistry is thirsty and fussy. You are running big circuits of aqueous and organic phases, you are washing, stripping, washing again. Water in, water out, and unless you want to buy fresh forever, you need to clean and recycle, which costs energy. Acid plants and lime trains are not subtle neighbors, they hum and hiss and truck in reagents that do not smell like fresh pine. If your mine is up a mountain with a tiny road and a village downstream that farms in a delta fed by your watershed, you are not just building a plant, you are building a relationship. That relationship lives or dies on the dull, daily competence of not spilling, not overdrawing, not forgetting that gypsum stacks and thorium drums are not just line items, someone's grandchildren will ask about them. You do not need moralizing to say this. You only need a calendar. We will go deeper into market behavior, magnet recipes, separation economics, and a few case studies where praseodymium quietly changed the outcome. For now, remember the bin in the magnet shop. The label says what it says because geology and chemistry made it so. Praseodymium is the green twin you get whether you asked or not, and learning to design with the mixture, embracing didymium in spirit, if not in name, is one of the grown-up moves in this business. Picture the control room at 2 in the morning. The solvent extraction banks hum like distant traffic. A technician taps a glass pH electrode against the side of a beaker and frowns. 30 millivolts off. Somewhere in the serpentine of mixers and settlers, the organic phase is stealing a little too much of the wrong lanthanide. It is not a disaster, it is drift. Drift is what turns a capable plant into an expensive one. And drift is what you fight, stage by stage, when the prize is the green twin hiding in a crowd that behaves almost exactly the same. Start at the beginning of the chemical hallway and walk slowly. If your feed is a bastnasite concentrate, the first insult you deliver is heat. Carbonate must be driven off, hydroxyls must be tamed, the rare earth phase must be made into a thing acids can chew without creating a gelatinous mess. If your flowsheet calls for a roast, you balance temperature so that carbon dioxide leaves briskly but the particles do not sinter into marbles that refuse to leach. If you acid bake, you watch the clock and the strength of sulfuric acid like a hawk, because too hot or too long and silica in the gang happily becomes a gel that turns your filters into pinatas, heavy, sagging, and useless. The goal is rare earths in solution and troublemakers in their own lanes. Iron should stay polite, aluminum should not foul everything it touches, calcium and magnesium, the classic freeloaders, should be managed so they do not co-precipitate when you start to change pitch. Then you invite the rare earths into the organic phase. The usual hosts have long names that sound like a chemistry quiz. Di2-ethylhexyl phosphoric acid is a workhorse, and they have a simple job, to prefer lanthanides over most other cations when the acidity is just so. They do not love equally. Heavier lanthanides tend to be more extractable under the same conditions than lighter ones, and this bias is what lets you lay out a train where one end collects lanthanum and cerium and the other end collects the likes of gadolinium and erbium. Cerium deserves a parenthetical. You can shove it out of the procession early by oxidizing it to the 4+ state, where it behaves like a stranger and can be precipitated as cerium dioxide. This is not just chemistry trivia, it is what opens the line to the twins you care about. Praseodymium and neodymium sit maddeningly close in every sorting metric the process uses. Their ionic radii are nearly twins, their hydration spheres behave the same, their complexes with organophosphorus extractants are separated by preferences, not chasms. So you do not separate them with a single flourish. You walk them through what looks like a city of stainless steel, with each neighborhood tuned to nudge the ratio a little more. In one bank you load, in the next you scrub, washing away impurities that came along for the ride, then you strip, persuading the organic phase to let go in a cleaner aqueous bath. Every time you do this, you are paying for tanks and mixers and pumps and instruments that do not show up in glossy investor decks because they look like plumbing. It is plumbing, and plumbing is where fortunes are made or quietly lost. Crud is the enemy that never appears in textbooks. Crud is the grainy, stubborn emulsion of organic and aqueous phases that forms when reality refuses to respect phase boundaries. It eats capacity, it traps your product, it clogs valves, and it attracts blame like a lightning rod. Crud comes from suspended solids the grinding and roasting steps did not quite control, from surfactant impurities in reagents, from accidental polymerization of extractants that have been heated and oxygenated one too many times. You deal with it by dedicating settlers to collect it, by skimming, by filtering, by swearing more than you planned to when you chose chemical engineering as a career. And while you wrestle crud, you watch the numbers that keep you honest, distribution coefficients, phase ratios, stage efficiencies. Those numbers never tell you praseodymium is special today. They tell you your system is drifting, which is the more useful truth. Monazite does not let you skip the hallway, it simply chooses a different entrance. Sodium hydroxide at high temperature and high concentration will crack the phosphate lattice, turning a refractory mineral into a friable mix. Phosphate leaves as trisodium phosphate in a liquor that, depending on your permits and neighbors, might be a product or might be a headache. Rare earths become hydroxides that you then dissolve in mineral acid to rejoin the same solvent extraction dance everyone else is dancing. The difference is radiological stewardship. Thorium and uranium ride with monazite like uninvited cousins at a wedding. You do not vilify them, you count them, capture them, and store them so that a decade from now you can still look at your balance sheets and sleep. There are plants that pretended this was an afterthought. Their grandchildren will not tell those stories as jokes. Eventually, with a patience that feels religious, you stand in front of a row of drums labeled neodymium praseodymium oxide, at a purity that makes magnet makers exhale. If your customer is willing to pay for a separate praseodymium stream, you run the twins through another gauntlet of stages that, by sheer bias and repetition, tilt the ratio until separate labels feel honest. Most shops stop at the blend, not because they cannot go farther, but because the market has decided that this is an elegant place to stop. You can build an entire business around that elegant stopping point. The magnet maker knows it, and so do you. Oxide is not a magnet. To get to alloy, you must make metal, or at least a metal-bearing feed that behaves like one inside an induction furnace. The orthodox route for these lanthanides is to turn the oxide into a fluoride, then let electrochemistry do the heavy lifting in a molten salt bath. Hydrofluoric acid has a reputation that is well earned, so you treat it with the respect you give a wild animal, and you react your oxides to make rare earth fluorides that behave properly in electrolytic cells. In the cell, a mix of alkali fluorides lowers the melting point and boosts conductivity to a sweet spot, and at the cathode the 3+ cations turn into atoms that rain down as a spongy, dendritic metal. The anode evolves gases you handle, not hand wave. When the cell runs well, you get praseodymium-rich metal in ingots that are not pretty but are honest. There is another route that magnet makers often prefer for flexibility: metallothermic reduction. Oxide, meet calcium under vacuum. Calcium, bless its heart, will take oxygen from almost anything if you heat and pressure it just right. What you fish out, after the reaction has run to completion, is a metal sponge and a calcium oxide slag. Break it apart, pick out the metal, clean it with a salt flux if you must, and now you can charge a furnace with praseodymium, neodymium, iron, and boron to make the alloy you actually care about. There are combinations: chlorides reduced with calcium, fluorides reduced in situ, little house recipes that earn their keep, but the concept is the same. You are trading electricity and careful molten salt control for vacuum, calcium, and very strong opinions about crucibles. Alloying for neodymium praseodymium magnets is a ritual with stages that matter in a way that feels fussy until you watch a torque curve wobble in a motor test. You melt the charge under vacuum or inert gas. You strip cast the melt into thin, rapidly solidified ribbons so that the right hard magnetic face forms with grains that will later accept orientation. Those ribbons go through hydrogen decrepitation. Hydrogen sneaks into the lattice and blows the ribbons apart along grain boundaries in a way that is almost gentle. The crumb that results is ground, usually by jet mill, into a powder with a size distribution that the press cares about. Under a strong magnetic field, you press the powder so that grains line up their easy axes of magnetization. You sinter to densify, carefully, so the grains do not coarsen into laziness. Then you anneal, because the crystal remembers heat like some people remember childhood. At the end of this, you have an oriented, dense piece that, after machining and plating, is a magnet. Praseodymium's role in this choreography is not to steal the show, it is to tweak the script. In the neodymium iron-boron structure, swapping some neodymium for praseodymium shifts the magnetic anisotropy and the temperature coefficient of coercivity by amounts that engineers care about in the real world. You are trading a little saturation magnetization here against a little thermal stability there, and those microtrades determine whether your inverter throws a fit when you push a car up a long grade in summer. The real trick comes at the grain boundaries. The way to make magnets survive heat without dumping inexpensive heavy rare earths is to treat grain boundaries like highways and diffuse small amounts of heavy rare earths, dysprosium or terbium, into them after sintering. That grain boundary diffusion pumps coercivity without poisoning the whole bulk with heavy rare earths that would lower magnetization. The matrix stays mostly neodymium and praseodymium, the boundaries get the armor. Praseodymium plays nicely with this approach. It does not block the highways, And in some alloy recipes it even helps sintering behave at temperatures that factories can hit with confidence shift after shift. Every step from oxide to finished magnet has a shadow market in scrap. In-process trimmings from machining are valuable because the alloy is valuable, and hydrogen decrepitation, obligingly, works on scrap as well as it works on ribbons. You can crack and remill, then blend back into powder feeds if you keep oxygen and carbon under control. End-of-life magnets are a harder story because they arrive contaminated with adhesives, plating, and the sins of their prior housing. Here again, a blend with praseodymium helps practically, because the market does not demand you separate at the element level to reuse. If the chemistry stays in bounds, you can funnel old neodymium praseodymium magnets back into new ones without becoming a tiny separation plant yourself. The economics are not heroic, but they are better than the alternative of landfilling what is, in essence, concentrated effort. If you zoom out to the supply chain and ask where the vice tightens, the answer is boring and therefore correct: separation capacity and metal-making capacity. There are far more projects that can plausibly make a mixed rare earth carbonate or oxide than there are facilities that can deliver clean, consistent neodymium praseodymium oxide every week of the year. And there are fewer still that can turn that oxide into metal and then into alloy at a scale that matters to the people who bolt motors into cars by the 100,000. This is why the bins in the magnet plant say neodymium praseodymium oxide, instead of two separate labels. The blend is not a failing, it is the seam where geology, chemistry, and economics have agreed to shake hands. On a map, that handshake is not subtle. There are many places that can mine a rare earth concentrate. There are far fewer places that can walk that concentrate through roast and leach and the long, humming hallway of solvent extraction to yield a clean blend of neodymium and praseodymium oxides, week after week, at volumes that keep the rest of the chain running. And there are fewer again that can turn that blend into metal and then into alloy and then into powder at industrial scale with the statistical consistency that automotive contracts demand. That is why a magnet maker's life is really three relationships, with a separator, with a metal and alloy shop, and with their own powder line. The mine is important, but it is upstream of where promises are kept. As of the mid-2020s, this funnel points overwhelmingly at one region. China alone accounts for roughly 69% of global rare earth mine production and about 85% of rare earth refining capacity, to say nothing of its dominance in magnet manufacturing. In practice, those three key relationships often lead to the same address. Price behavior reflects this geography of control. The market rarely quotes a price for praseodymium alone, it quotes a price for the mixture of neodymium and praseodymium, often called NdPr, which is the thing most buyers actually consume. That price moves with a mix of fundamentals and theatre. Fundamentals are dull and decisive: electric vehicle production schedules, wind turbine orders, maintenance cycles at separation plants, production quotas and environmental inspections that nudge output up or down. Theatre is everything else: inventory builds ahead of policy rumors, nervous destocking when a battery maker whispers about switching motor technologies, traders rediscovering rare earths every few years as if it were a new hobby. The two mingle. The price climbs when separation capacity is tight or when new alloy lines ramp faster than oxide supply. It sags when buyers overpurchased and need to sit on their hands for a quarter. It spikes when a policy change lands on a thin market. It drifts when nothing dramatic happens but demand ratchets up by a quiet 5 or 10% and nobody noticed until the bins got light. Volatility has a habit. It overshoots. The rare earth spike in 2010 and 2011 taught a generation of engineers how to thrift heavy rare earths in magnet designs and how to switch temporarily to magnet-free motors when they had to. Those lessons never really leave a field. Today, when the mixture of neodymium and praseodymium tightens, the first move is not panic, it is substitution at the margins and inventory discipline. The last decade hardened buyers. They do not want to play hero in a commodity story, they want 2 to 3 months of stock and no drama. If they have learned anything, it is to buy a little insurance when prices are sane. For instance, neodymium oxide's price sprinted from under $50 per kilogram in 2020 to well over $130 by early 2022, then jogged back into double digits by 2024 as new supply came on and demand blinked. That roller coaster taught customers to keep some breathing room in their budgets and cupboards. Contracts reflect that new education. The big consumers of neodymium and praseodymium, magnet makers feeding automotive and wind, prefer long-term offtakes with price adjustment formulas more than spot fireworks. A common pattern is a base price tied to a published index for the blended oxide, converted through agreed conversion factors into metal and alloy pricing, with surcharges for oxygen control and trace element specs. The buyer gets predictability, the seller gets cash flow visibility, both get to sleep. Spot still matters, especially for glass and ceramics and 1,000 small industrial uses, but the power sits with the buyers who can sign 5-year deals and mean it. If you want to understand why praseodymium keeps its place in the magnet world, you have to look at the designer's threshold decisions. A motor designer does not wake up wanting a specific element. They start with a torque target, a power density target, an efficiency envelope across a temperature range, a cost cap, and a space constraint that is non-negotiable because the rest of the car has claimed the real estate. In that optimization, permanent magnets with a neodymium and praseodymium backbone win because they pack a lot of magnetic energy in small spaces and keep that energy when hot, provided you treat the grain boundaries properly. Ferrite magnets are cheaper per kilogram, but when you scale a motor up to match performance, the extra copper, steel, and volume claw back the apparent savings. Samarium cobalt magnets keep their heads at higher temperatures and laugh at corrosion, which is why they show up in aerospace and in places where failure is unacceptable, but they cost more and saturate lower than the best neodymium praseodymium alloys. Magnet-free motors, induction or switched reluctance, delete the rare earths and add complexity in control systems and changes in efficiency and weight that carmakers count in miles of range and kilograms of mass. The threshold where a designer abandons neodymium and praseodymium is not a single number. It is when the penalty in weight and efficiency exceeds the penalty in price and supply risk for their specific product. That threshold is stubbornly high in passenger cars and in most wind turbines, which is why the green twin keeps getting invited back to work. Inside magnet design, thresholds multiply. If your duty cycle is hot and harsh, you might add dysprosium or terbium at grain boundaries to armor coercivity. That is a luxury because heavy rare earths are expensive, and the whole field learned to use them like truffle oil, sparingly and in the right places, after 2011. Blending praseodymium with neodymium is one of the gentler knobs. The substitution shifts anisotropy and temperature behavior enough to keep magnets out of trouble in motor bays that bake. You are not changing the music, you are changing the key to match the singer. To put that luxury in perspective, the heavy rare earths have been an even more exclusive club. Until very recently, China accounted for about 99% of the world's separated dysprosium and terbium supply. Only in mid-2025 did any operation outside China, an Australian-owned plant in Malaysia, produce its first kilos of dysprosium oxide at commercial grade. That was a milestone, but more symbolic than transformative. No wonder heavy elements are used like saffron. There is a quieter application world where praseodymium's wins have nothing to do with drive trains. In glass and ceramics, those narrow electronic transitions in the F-shell turn praseodymium compounds into meticulous colorists. If you want a red glass that reads as true red under daylight and not as a tired brown, a whisper of praseodymium will get you there. If you want to see past the orange-yellow glare of sodium in a hot flame, you put praseodymium with neodymium into goggles because they swallow that glare while letting the rest of the world through. In lighting, praseodymium feeds emission lines that fill awkward gaps in spectra. In magnesium alloys for aerospace, a pinch of praseodymium shifts creep behavior and helps parts hold shape in heat. None of these markets are as gluttonous as magnets, But they matter because they diversify demand and because they highlight a theme. Praseodymium is a tuner, and tuners have work in any orchestra. Recycling is where optimism meets metallurgy with a thud and then stands up again. In-process recycling works beautifully. If you are machining magnets, you catch the swarf, you hydrogen crack it to pieces, you remill, you blend back into powder, and as long as oxygen and carbon are controlled, you are back in business. The closed loop is tight because the alloy is known, the contamination is manageable, and the timing is immediate. Post-consumer recycling is harder. Old magnets come glued into assemblies with adhesives that carbonize, plated with nickel that does not respect your solvents, and fraternizing with steel, copper, and plastic that all want to come along for the ride. There are two paths. One is direct recycling, hydrogen decrepitation, remilling, and reusing without breaking down to elements. It is elegant when you get a clean feed of similar grades. The other is full hydrometallurgy, shred the devices, liberate the magnets, dissolve, separate, and remake the blend. The second is chemically honest but capital hungry, and it makes you, effectively, a smaller version of a separation plant. In the near term, the practical contribution of end-of-life recycling to supply is modest, not for lack of ingenuity but for lack of clean, concentrated, and predictable feed. Over time, as more motors retire and as collection improves, the numbers grow. For now, the green twin mostly returns as shop scrap and as occasional treasure from well-sorted waste streams. Environmental and social constraints are not a separate chapter, they are the operating system. The separations hallway drinks water and eats electricity. The acid plant whispers to your neighbors on the wind. Neutralization creates gypsum stacks that will outlast your board of directors. If monazite is in your diet, thorium-bearing residues will sit in drums with labels that have to look responsible. For decades. All of this is manageable. None of it is free. The projects that succeed are not the ones with the prettiest core photos, they are the ones with a water balance that closes without magical thinking, with a power contract that survives summer, and with a waste plan that treats the word perpetual with the seriousness it demands. Life cycle assessments consistently show that most of the energy use and emissions for a neodymium praseodymium magnet are bound up in separation and metal making. That is where gains matter. Better reagent stewardship, tighter water recycling, cleaner power for electrolysis and furnaces, these are the levers that move the footprint, not a clever press release. Geopolitics peeks in the window whether you invite it or not. Separation capacity is concentrated, and concentrated capacity is exposed to policy. Production quotas and environmental crackdowns inside a country with many of the world's separator banks ripple into the price for the blend everywhere. Export documentation rules and licensing regimes add friction, and friction becomes price. In 2025, China turned that friction up a notch by slapping export license requirements on a slate of heavy rare earth compounds and magnets. For a moment, European automotive suppliers murmured about looming shutdowns, until trade dialogues produced a green channel to expedite licenses for key buyers. The hint was clear: if one entity holds most of the funnel, it can squeeze it when it chooses. Meanwhile, automakers and turbine makers in North America, Europe, Japan, and elsewhere sketch arrows on maps from future mines to future separators to future magnet plants and discover how hard it is to will a hallway of solvent extraction into existence on a timetable measured in election cycles. The result is strategic redundancy. Companies try to qualify second sources, countries set targets for domestic capacity, everyone promises offtakes to coax financing across the line. Indeed, governments have begun putting real money behind these hopes. In mid-2025, the United States Department of Defense wrote a check for roughly $400 million to help one domestic producer expand from mine to metals to magnets. Around the same time, an iconic electronics company inked a $500 million deal to secure rare earth magnets made from recycled materials on American soil. These moves were applauded as steps toward resilience, though everyone involved knows how much distance remains between press releases and tons per year. Praseodymium is not plotting, it is merely sitting in the middle of this, doing what elements do while humans argue about sovereignty. A quick case study, without names. An automaker tried to dodge rare earth exposure by switching a mainstream electric vehicle platform to a magnet-free motor. The first prototypes looked fine on a dynamometer in an air-conditioned room. In full vehicles, in summer heat, the mass penalty and the efficiency penalty shaved range in a way that marketing could not spin. The team throttled back ambition. They put permanent magnets back into the higher trim models where customers would feel the loss most acutely and kept the magnet-free motor in a variant where the compromise was acceptable. Inside the magnet, the blend of neodymium and praseodymium did not change because the physics did not change. The green twin did not win by force, it won by making the rest of the system easier. Another case, this time at the supplier end. A separation plant bet heavily on pushing praseodymium and neodymium apart to sell both streams at a premium. On paper, the economics sang. In practice, the extra solvent extraction banks and the tighter control loops ate up time. Customers started to complain about delivery slippage. The plant stepped back and declared victory at the blend. It sold a clean neodymium praseodymium oxide and improved its reliability. The premium for separate praseodymium lived on spreadsheets, the value of never missing a truck lived in reality. That is not a failure of chemistry, it is an alignment with how magnets are actually made and bought. When you hear substitutes invoked, ferrite magnets, samarium cobalt, induction motors, switched reluctance, listen for where the substitution boundary actually sits. It is rarely at the level of a part number. It is usually at the system level, where a heavier, less efficient motor forces a bigger battery or a smaller trunk, or where an exotic magnet with wonderful high-temperature behavior demands a unit price that makes accountants develop migraines. Praseodymium holds its seat in designs because it keeps the rest of the system out of trouble. That is a boring reason. It is also the best kind. Market structure will keep encouraging that boring reason. As long as neodymium and praseodymium flow together from rock to oxide to alloy, the blended price will be the heartbeat. As long as separation capacity is the scarce talent, buyers will care less about which minor marketing team shows on a slide and more about who runs the mixer settlers and the metal furnaces. As long as automotive and wind demand grow in steady, unromantic increments, the bins in magnet plants will empty and fill with the cadence of a factory, not the drama of a copper strike. In that world, the green twin prospers by being second in command in the right army. It is not the face on the poster. It is the tuning that makes the poster look competent. And that purchasing manager's superstition. It pays for itself. The label on the bin is what it is because geology bundled praseodymium with neodymium and because chemistry made unbundling expensive. Read the label, and you remember the rules. The price you negotiate is for a mixture. The bottleneck you must respect is a hall of solvent extraction. The risk you carry is not exotic, it is scheduling and quality. Praseodymium does not need to be a diva to matter. It only needs the system to keep working, which is what good supply chains try to do when nobody is watching. The test cell is warm, the dyno howls, and the engineer with the clipboard pretends not to hold her breath. The new rotor geometry is in the chamber. Same inverter. Same stator windings. Same duty cycle. The only change is invisible, a slightly different share of praseodymium in the magnet recipe and a long afternoon of grain boundary diffusion that the metallurgists swore would buy a few precious degrees Celsius of composure. The trace on the screen wobbles less as the temperature climbs. The torque droop the team hated last week is now a gentle slope. No one cheers. Someone writes, acceptable, in a box. That is praseodymium's favorite compliment. Walk that performance trace backwards to the ground. The particular magnet that makes this graph behave is the end of a chain that looks straightforward on a slide and serpentine in real life. Start with a carbonatite body where bastnasite grains carry the light lanthanides. Drill, blast, or crush. In the concentrator, bubbles insist on gossiping with the wrong minerals unless you dose and condition and pester the slurry until bastnasite decides to float like it promised. A concentrate leaves the plant and heads to a roaster where carbon dioxide and water depart first, and the rare earth phase becomes susceptible to the attentions of acids without turning the whole mess into silica pudding. Roasted material meets sulfuric acid, heat and time do their slow work, and now the rare earths are in solution, together, like a choir you must teach to sing in parts. Somewhere far from the pit, rows of mixer settlers hum. In one line, oxidized cerium loses its place and leaves as an oxide that behaves like it has somewhere else to be. In the central banks, the twins, neodymium and praseodymium, refuse to take separate cabs. Operators accept the truth most of the world already learned: sell the blend. Drums of neodymium praseodymium oxide roll out of the plant with certificates that speak in quiet absolutes: total rare earth content, trace metals in the parts per million, loss on ignition that hints at oxygen or adsorbed water you do not want to carry into a melt. A metal shop converts the blend into a feeder furnace understands. In one building, an electrolytic cell glows like a small orange sun while a molten salt eats at crucibles and returns praseodymium and neodymium to their metallic state. In another, vacuum and calcium reduction steal oxygen from oxides and hand you a spongy metal and a slag that breaks apart like stale bread. The ingots are not pretty. They do not need to be. They must be consistent. A magnet house with a sense of humor calls these ingots unphotogenic but honest, and charges them into a furnace with iron and boron to make the master alloy that matters. Strip casting splashes the melt into thin ribbons that freeze fast enough to trap the right hard magnetic phase. Hydrogen sneaks in later to break those ribbons along their boundaries into a crumb that a jet mill can worry down into a powder with the size distribution the press insists on. Under a magnetic field, the powder falls into alignment. Pressure gives it shape. Sintering gives it density. An anneal persuades the crystal to relax into the state that will not betray you when hot. The magnet is born, but not yet trustworthy. You machine to tolerance. You coat against corrosion. You diffuse a hint of heavy rare earth down the grain highways to armor coercivity where the magnet is weakest. All along, the recipe holds a quiet constant: neodymium and praseodymium together, in a ratio the plant can deliver every shift of every week. Put that magnet into a rotor and the earlier graph makes sense. No miracles. Just less panic when the temperature needle drifts right. The point is not that praseodymium is heroic. The point is that praseodymium keeps the rest of the system from needing heroism. Now for a company pivot that actually earned its keep. A magnet maker had made a religion of chasing maximum energy product at room temperature because the room was where the brochures were written. The cars, unfortunately, lived in summer. Warranty data whispered that demagnetization events clustered on hot days under heavy load. Engineers did not abandon performance, they changed the way they defined it. They shifted from a monoculture of neodymium-forward alloys to blends with more praseodymium, paired with a disciplined grain, boundary diffusion of dysprosium targeted precisely where it did the most good. Coercivity climbed at the temperatures that mattered. Saturation magnetization dipped a little, on paper, in a way no driver could feel. Field returns dropped. The pivot was not a press release. It was a revised spec sheet and a test cell that stopped producing heartburn. The lesson is not about any single element. It is about treating performance as a landscape, not a vertical line through one number at 25 degrees Celsius. Consider a mine-to-market chain that looked tidy on day 1 and complicated on day 2. A company built its flowsheet around bastnasite that behaved beautifully in bench tests and pilot plants. In commercial grinding, liberation lagged because the ore changed faces across the first benches of the pit. Too much fluorite floated with the bastnasite. The roaster handled the change without fanfare. but the acid plant did not. Fluorine slipped into circuits where it was not invited, extractants aged faster than they should, and the settlers developed the kind of interface moods that make operators talk to inanimate objects. The fix was not a new solvent or a new philosophy. The fix was geology. The mine plan shifted back to the benches that delivered the mineralogy the plant was commissioned to see. Throughput bounced. Quality settled. The valuable revelation was not, chemistry is hard. It was, the plant and the pit are a couple, do not let them sleep in separate bedrooms. A fiasco, because those teach quickly. A monazite processor in a wet country decided that thorium management would sort itself out later because early shipments were small and early cash flow soothed many anxieties. Later, arrived on a rainy week when neutralization tanks were already busy with sulfate-rich streams. Drums that should have been on concrete pads under covers were instead in a hurry under tarps. The neighbors did not care about the technicalities of gamma versus alpha. They cared about the sightlines from their kitchen windows and about the word, permanent. Regulators, who can read a calendar and a weather forecast, took a conservative view. Operations paused. The company brought in serious people to engineer the storage the original plan had sketched with a light pencil. It cost more than playing pretend. The only surprising thing about the story is that anyone was surprised. Monazite is chemistry plus stewardship. If you skip the second, the first becomes a courtroom drama. Zoom back to magnets, because that is where Praseodymium's rent gets paid most often. Designers manipulate more than the lanthanides when they tune coercivity and temperature behavior. Small additions of elements like aluminum, copper, niobium, and gallium adjust grain growth, phase stability, and boundary chemistry. Those additions are not fashion, they are levers. Praseodymium harmonizes with those levers in alloys that target high power density at elevated temperatures. It is not that neodymium alone cannot do the job. It is that the shared job becomes easier when the twin with the greener temperament is in the room. The datasheets will not say it that way. The dynamometer will. There is another, quieter chain in which Praseodymium earns its living: glass, lasers, and ceramics. A glassmaker making a true red that stays true under daylight does not need kilograms, they need consistency and the right oxidation state at the right moment in the melt. Praseodymium slips into the lattice and makes color feel like physics rather than marketing. Specialty lasers that want specific wavelengths lean on praseodymium-doped hosts that sing at those exact notes. Ceramic pigments that defy ultraviolet light and weather owe their stubbornness to those narrow F-electron transitions that age slowly. These markets are rounding error next to magnets, but they are also the reason you cannot think about praseodymium as a one-trick element. The same electrons that make motors less nervous also make a glass of a certain red that keeps its dignity at noon. Recycling, to be useful here, has to be described without romance. Inside a magnet house, in process scrap is a bankable resource. Hydrogen decrepitation turns whole rejects and machining swarf back into feed with minimal drama. Oxygen and carbon are watched like hawks, the blend of neodymium and praseodymium is preserved rather than unscrewed, and the loop closes in days, not months. End-of-life recycling is a different animal. The stream is heterogeneous, the magnets are glued into things, nickel plating refuses to mind its manners, and plastics complain when you heat them. Two approaches share the stage. Direct reuse breaks the magnets down and reforms them without trying to return to elements. Hydrometallurgy throws the net wide, dissolves, separates, and rebuilds. The first is elegant when you control feed. The second is honest when you do not. Neither is a silver bullet. Both will matter more later than now, simply because there will be more to collect later than now. For the next few years, the green twin mostly returns to service as shop scrap with a short commute. What does control look like when the world truly needs more of this mixture? It looks like separation plants that run every week of the year without excuses, metal shops that treat oxygen specification as a creed, alloy lines that never drift, and magnet houses that make waste a rounding error. It looks like water recycled until the only fresh you need is what chemistry truly consumes. It looks like power contracts built on stable, clean supply so that every kilowatt-hour that went into pushing electrons around in a solvent extraction bank and an induction furnace does less damage on its way to the torque curve. There is nothing mystical in that list. It is the sort of boring competence that makes everything else look visionary. Downstream, the purchasing people who staged the miracle of acceptable on the test cell screen do not want to be heroes. They want bins that never run dry, oxygen numbers that never creep, and a blended neodymium praseodymium oxide that never surprises them. They want their long-term offtakes to cover the volumes that really run, and they want a second source that is truly qualified rather than politely promised. If they have learned anything since the spike a decade and a half ago, it is that hedging inside the design, being comfortable with a blend rather than insisting on a single element, being good at grain boundary diffusion rather than naive about it, pays for itself when markets twitch. Praseodymium's role in that hedge is not glamour. It is flexibility. One more mine-to-market thread that matters because it feels unsexy: logistics. The oxide drums that left the separator on a Tuesday have to land at the metal shop before the weekend because an induction furnace does not care about your excuses. Incoterms suddenly become the most interesting words in your life. Export paperwork has to be exactly right because a customs hold turns a neat material balance into a scheduling disaster. The stenciled words on the drums, neodymium praseodymium oxide, are the same everywhere. The route they travel is not. Ports differ in how they treat chemicals, and trucks do not arrive faster because you tap your foot. Everyone in the chain learns, eventually, that the technical bottleneck sits in the separations hall and the practical bottleneck sits wherever a bored person with a stamp thinks your form looks weird. Good suppliers budget for both. If you listen carefully, there is a tone that separates operations that last from operations that do not. The lasting ones talk about water balances and pH control and the feel of powder under a field alignment press with the same affection some people reserve for sports. They speak about praseodymium without mystique because they do not need mystique. The metal is a co-worker, not a mascot. They do not search for purity where utility lives in mixtures. They do not chase a dazzling room temperature number when customers drive in summer. They prepare for what the material is likely to do on a Tuesday at 2 in the afternoon when the plant is a little tired. The green twin, in that world, is not a riddle. It is a habit. There is a whiteboard in a windowless room where the future of magnets gets drawn and erased 5 times a week. The axes are not art, time along the bottom, temperature and torque on the side, and a few colored lines for the things that turn into money. Someone has scrawled 3 phrases that matter more than any glossy strategy deck: grain boundaries behave, oxide arrives, and customs does not get cute. That is the whole story, if you say it fast. If you say it slowly, praseodymium sits at the hinge, the quiet decision that makes the rest of the machine less needy. Before we sketch futures, let us close a few loops that always come up in the hallway after a talk like this. First, the rumored magic flow sheets. Yes, ion exchange resins with more personality than the old standbys are making headway. Yes, membranes that promise to notice the tiny differences between lanthanide cations are walking from pilot to demonstration. Yes, double salt crystallization schemes exploit the way rare earths and sulfates and nitrates prefer certain dance partners at certain acidities. All of that is real, none of it is a wand. The test they must pass is not elegance. It is Tuesday afternoon when the power blinks, one reagent arrives off-spec by a hair, and the feed grade shifts because the mining crew cut a slightly different bench. If the pilot plant ran across a winter, through inventory cycles, and with operators who learned the system on the job rather than in a lab coat, I get interested. If it made kilograms in spring sunshine and a good mood, I clap and wait. Praseodymium does not mind either way. It will ride whatever process works at tonnage across seasons. That is the only kind of victory that counts. Second, the notion that a glass or ceramic pathway could become material to demand. Almost never. The color and optics work is meticulous and profitable on a per kilogram basis, but on a tonnage basis it is a rounding error next to magnets and will stay that way. The aerospace magnesium story is similar. It matters to the people bending the metal, it matters not at all to the people filling bins at a magnet house. Keeping those scale differences straight saves you from bad headlines. Third, the whisper that tetravalent praseodymium chemistry will unlock something spectacular. It unlocks interesting oxide behaviors and some catalytic tricks, but it does not rewrite the magnet chapter. The 3+ state is still the citizen that pays taxes and wins elections. If a process salesman leads with chemistry adjectives rather than with an uptime graph for their plant, return them gently to earth. All right. Futures. It is August 2025. The question that serious people actually need answered is not whether praseodymium is critical. The question is how often it will be the thing that causes meetings to be rescheduled between now and, say, 2032. You do not need a cinematic list. You need a handful of explicit scenarios you can bet against, with drivers and odds that will not embarrass you when you revisit them in 3 years. Base case first, because boring is usually right. Through 2029, electric vehicle production ratchets up without fireworks, wind additions drift higher in steady steps, and permanent magnet content per motor nudges down a little as designs get thriftier at the edges. Several separator expansions that have been quietly under construction since 2023 come online in stages, not in trumpets, and the drumbeat of neodymium praseodymium oxide shipments grows with the predictability of a decent factory. The price of the blend breathes when inspections and quota adjustments in the big separator country cause brief slowdowns, but breathes rather than wheezes. Alloy and metal capacity proves to be the tighter turnstile a few times, which pushes merchants to hold slightly more inventory and gives oxide sellers the occasional chance to smile. In this base case, schedule risk on car platforms comes from inverters and software bugs more often than from magnets, and the purchasing manager's label ritual remains superstition rather than therapy. Call the probability around 60%. Drivers, separation projects that are already financed and largely civil, complete actually commissioning, automotive learning curves about inventory discipline sticking, and policymakers discovering that speeches about domestic capacity are not the same as commissioning dates on a calendar. A tighter case, because the world rarely stays that polite for an entire decade. In 2026 or 2027, environmental enforcement inside the jurisdiction that hosts a chunky share of separation capacity tightens in a serious way, not as political theater but as a genuine corrective to sloppiness. Several plants slow for retrofits at the same time a couple of new car platforms ramp faster than their own conservative forecasts, because consumers finally decided that ranges and prices crossed into good enough territory. The blended oxide market thins to a taut rope. Prices jump in the way that causes old charts from 2010 to make the rounds again. Magnet design teams do not panic, but they do trigger all the levers they practiced. Slightly more praseodymium against neodymium when that buys thermal grace, stricter grain boundary diffusion protocols, swapping a few lower trim variants back to magnet-free motors for a season, and a polite but firm set of phone calls to suppliers reminding them what an offtake contract is. The squeeze lasts 3 to 5 quarters, not 3 to 5 years, because capacity does not vanish, it refurbishes. The people who suffer most are those who are counting on spot miracles. Everyone else notices how much less fragile the system is than it felt in 2011. Call the probability 20%. Drivers, genuine clampdowns rather than headlines, early retirement of ancient separation banks that were one inspection away from a sabbatical, and a run of hotter summers that make thermal margins feel tighter in test cells than they did on paper. There is a glut case, because humans overbuild when they smell policy money. Between 2027 and 2029, more non-incumbent separation capacity actually lands than the sober among us expected. Some of it was real engineering, some of it was subsidized enthusiasm finding competent partners. At the same time, magnet content per motor inches lower faster than planned because a few large platforms switched to motor topologies that do the same work with 5 to 10% less magnetic energy density, and grain boundary diffusion recipes keep getting smarter. A couple of high-profile wind projects slip their schedules to the right for reasons that have nothing to do with magnets and everything to do with grid interconnections and permitting. Drums stack a little higher than anyone wants to admit. Prices soften beyond the comfort level of balance sheets that assumed permanent tightness. The survivors are the separators with the lowest operating costs, excellent water and power contracts, and the least romantic view of their maintenance schedules. The ones that skid are the ones who built for press releases and counted on heroic prices forever. Call this 15%. Drivers, civil works that finished on time in 3 places that usually do not, slower grid hiccups that ripple back into turbine orders, and a brief bout of fashion in motor design that trims magnet volume without trimming performance in ways customers can feel. There is a substitution surprise case, which is only surprising if you stopped paying attention after graduate school. Between 2028 and 2031, control algorithms and semiconductor devices keep improving to the point that switched reluctance and induction motor topologies claw back more share than polite magnet makers expected in a few segments where price pressure is severe and sound and feel penalties can be tolerated or masked. In commercial vehicles where cabin noise is already a negotiation, in low-range city cars where efficiency penalties are paid back by cheaper batteries, and in some robotics niches where design freedom is broader, magnets lose a thicker slice of demand than the base case assumed. It is not a rout. It is a notable trim. Since separation capacity was being built on the assumption that everything would keep pulling straight up and to the right, the market feels overserved for a couple of years and behaves accordingly. Call it 10%. Drivers, silicon carbide and gallium nitride devices getting cheaper and tougher, customer tolerance in a few segments being higher than assumed, and designers rediscovering that weight saved in one subsystem can be traded for weight added in another without anyone crying if the whole product remains delightful. You noticed the math. These 4 sketches sum to 105 if you are not careful with your rounding. That is fine. Futures are smudged chalk, not chiseled stone. The point is not that one of these will land exactly. The point is that none of them require magic, and the differences in them come from the same handful of levers: separation uptime, alloy and metal conversion capacity, design thrift in magnets, the motor topologies that platform engineers favor, and the pace at which power electronics keep getting better. Let us tuck 2 more concrete stories in here, because anecdotes are how complicated systems introduce themselves. A wind original equipment manufacturer made a bet in 2024 that gearboxes were making a modest comeback on cost grounds. They were right in 2025. They were wrong by 2027 when warranty data pointed to downtime penalties that wiped out the capital savings. Their pivot back to permanent magnet direct drive looked, from the outside, like indecision. From the inside, it was math. They did not apologize to magnets, they apologized to their own service teams who were tired of climbing towers in February. The blend of neodymium and praseodymium did not change because physics did not change. What changed was the cost of being clever. A separation startup in a coastal jurisdiction announced an anodyne word salad in 2023, novel membranes, game-changing selectivity, minimal footprint. They were sincere and, to their credit, technically ambitious. In 2026 they were still operating, which already puts them in a rare club. Their plant worked when the feed was clean and the temperature was their favorite. It faltered when monsoon rains changed the water chemistry enough that a dozen small parameters drifted in the same direction. They stabilized by installing, without advertising it, a boring solvent extraction train to do the coarse split before the membranes did the fine work. Their investors were confused. Their operators were relieved. Their customers stopped asking about the word novel and started asking about monthly volume. Lesson learned: the best place for novelty in critical materials is one notch downstream of a conservative step that keeps the lights on. We should talk explicitly about where control sits, because that is how you decide where to spend scarce competence. It does not sit in the board approvals for a mine. It does not sit on a brochure that shows strip-cast ribbons. It sits in separation plants that do not drift and in metal shops that treat oxygen and carbon as holy writ. It sits in how carefully you manage water and reagents so that you are not forced into shutdowns by your own waste. It sits in logistics paperwork that is as exacting as your pH control. It sits in the habits of engineers who know that grain boundaries remember the last 10 degrees and the last 5 minutes, and who treat those memories with respect. You cannot buy that control with adjectives. You buy it with practice. Substitutes are a favorite parlor game, so let us be precise about thresholds rather than coy. If ferrite magnets are free, they still do not win when power density is king and space is tight, because the copper and steel you muster to make up performance cost you range and weight. If samarium cobalt is indestructible at high temperature, it still does not win in mainstream automotive when the cost per unit mass refuses to blink, because customers notice price more than they notice the elegance of surviving one more 10 degrees Celsius. If a magnet-free motor deletes rare earths, it still does not win a family car if the 2% hit on efficiency at highway speeds turns into 8 miles of range that the marketing team cannot hide. The thresholds move in small amounts, not in leaps, and praseodymium remains inside the winning side of those thresholds more often than not because it helps the magnets behave where the magnets actually live, which is in heat, vibration, and company. There is a social dimension to this element that deserves one last, clear sentence. Praseodymium is not a solitary strategy. It is a way to make a mixture do exactly what you need without making the rest of the system nervous. That sentence is worth more than any market forecast. It explains why magnet houses specify the mixture rather than the pure metal. It explains why separation plants draw the line at a blend and call it a day. It explains why motor designers can sleep when the weather is hot and customers are impatient. It also explains why people who fall in love with single-element stories miss how industry actually works. Water, energy, and neighbors. We cannot leave without saying the quiet part one more time. The only credible definition of sustainable magnets is magnets made with separation banks that run on clean power, with water circuits that are closed and disciplined, and with waste that is stored like a solemn promise rather than like a suggestion. If monazite is in your diet, thorium is in your family. Act like an adult about it. If your reagent trucks drive past schools, your community relations are chemistry. When you hear life cycle assessment, do not roll your eyes. Read it like a P&L for physics. It tells you where the energy use and emissions actually live. Spoiler, they live in your hallway of separations and in your metal furnaces, not in the marketing copy on your website. You may be waiting for the teardown of an automaker's claim that they have a magnet-free future. There is nothing to tear down. They will build cars both ways. They will put the magnet-free motor where it makes sense, and they will put the neodymium praseodymium magnet where it keeps the rest of the car honest. The green twin is not offended. It is busy working. The only people who get embarrassed are those who insist on absolutism in a world that pays for nuance. One last vignette, because the craft deserves it. A powder press operator in 2028 watches the flow of a new lot and does not like the way it fills the die under the alignment field. The oxygen number is fine, the carbon is fine, the lot passes everything on paper. But the way the powder slumps and the sound it makes when the punch kisses the fill says the grain shape has drifted. The magnet house calls the alloy line, and the alloy line admits they let one pour cool a touch too slowly before strip casting because a cooling circuit was sulking. The next pour corrects it. The press operator nods and goes back to not being a hero. The torque curve in the test cell 2 weeks later is as boring as a straight edge. The green twin does not get a mention in the meeting. That silence is the tell. When praseodymium is not in the conversation, it means everything upstream did its job. Back to the windowless room and its whiteboard. The colored lines are still there, slightly smudged from last week's hands. The team talks through the 4 futures and their own versions of them, because every company lives on a slightly different slope of demand and comfort with risk. They assign odds. They argue about whether 2027 is the year the pinch arrives or the year the glut begins. No one pretends to know. They do something better. They prepare their systems so that any of those futures is survivable and 2 of them are quietly profitable. They do not bet the company on a purity that the world does not buy. They bet on a mixture that the world already trusts. They bet on praseodymium being exactly what it has been since the day the old didymium myth fell apart, the green twin that makes the loud twin easier to live with. So here are the wagers, spoken plainly so they can be revisited without excuses. The steady case, capacities add, magnets stay central, prices breathe rather than gasp, is about 60% through 2029. The temporary squeeze driven by enforcement and retrofit is about 20% across a stretch of 3 to 5 quarters before 2028 is over. The overbuild and soft patch case as new capacity gets ahead of itself is 15% for a year or 2 just as the second half of the decade closes. The substitution surprise that trims a noticeable slice of demand without changing the center of gravity is about 10% and does its work between 2028 and 2031. The probabilities do not add to a sermon. They add to a posture. Keep the blend on hand, keep your diffusion recipes tight, keep your water and power honest, and treat paperwork as part of metallurgy. If that sounds unsentimental, good. Materials do not reward sentiment. They reward people who say what the label on the bin says out loud and then build accordingly. The label says neodymium praseodymium oxide because the rock and the chemistry and the economics shook hands and wrote it that way. The green twin has been telling you the truth this whole time.